this function for generic reference probability measure mu with bounded density, and then we're going to draw some consequences of that. So as I was explaining, I'm trying to find a way to renormalize the singular aspect of this energy. And the renormalization is going to be done by smearing the charges. So another way to present it, which is in some sense easier, is to say we're going to truncate the potential. So let me introduce the following. Given some parameter eta, which is going to correspond to the length scale of the smearing, we're going to define g eta to be the function g truncated at level eta. Okay, so it's the mean of g of eta. Okay, so you remember g is some inverse power or log. Okay, so g of x, 1 over s, x minus s, or minus log x. And this is defined for points in Rd, but of course you can extend this to a function for real numbers. Just use the same formula. Okay, so when I say g of eta, I mean eta to the minus s over s, or minus log of eta. And so g eta is a function whose graph is this. Okay, so you truncate like that. So it's no longer singular. Okay, so this is g eta. And we're also going to let f eta denote the difference g minus g eta. So it's f eta is kind of the tip, right? So f eta is like that. And this is size eta. Okay, so this one is now a continuous function. Okay, it's not smooth because of the angles here. You could make something smooth if you want. It's not very important. This one is now continuous, and this one remains singular, but now it's compactly supported. Right, so this one is supported in ball of center 0, radius eta. And moreover, g eta coincides with g outside of the ball of radius eta, so this is all trivial. And what is the Laplacian of g eta? So we're in the Coulomb case, right? Try to remember. Well, so the Laplacian is outside of this ball of radius eta, g equals g eta, so the Laplacian is 0. Inside the ball, the function g eta is constant, so the Laplacian is 0. So where is the Laplacian? It's on the boundary of the sphere. It's on the boundary of the ball, so it's on the sphere. Moreover, everything being radially symmetric is going to be a uniform density on the sphere. So what we can say is that this thing is equal to the same constant CD times a measure that I'm going to denote like this, delta 0 eta, or delta 0 eta is the uniform measure of total mass 1 on the sphere Okay, you can check that in the sense of distributions if you want. Or you can just argue by this symmetry that it has to be the case. And so in particular, one thing that's nice here is that if you convolve G with delta 0 eta, what is it? This being the fundamental solution, this function is going to have to be the function whose Laplacian is equal to this one. But so that's the function. Okay, so this is G eta. All right, so this is just to say that for particular smearing, we take the one that's pushing everything on the boundary of the ball, of the sphere, because it's convenient. It generates a potential which is uniform in the ball, and that's kind of nice. Other choices are possible. You can make a uniform distribution on a ball, and that's fine. You can make a smoother distribution. It works as well. Okay, so now that we have defined this truncation, instead of Hn, so if you remember, we were defining Hn to be the potential generated by the points and the background and mu. What we're going to define, given some vector eta, which is a vector of parameters eta 1, eta n. So I have n points. So I want to give myself n radii, eta I. We're going to let Hn eta be the same thing, but where I replace the deltas by the smeared deltas. Okay, so one thing that we introduce here is this flexibility, the idea of having smearing radii which may depend on the points. It's going to be useful later. Okay, so you give yourself n points, and you pick a radius for each point, maybe not the same. And now we have this truncated potential. And we note that Hn eta is also the same as Hn minus the sum of the f eta I of x minus xi, where f eta I are these tips here. Right? So in fact, to obtain h eta, because of this relation, to obtain Hn eta from Hn, what you have to do is you basically have to subtract off these infinite tips from the potential. Okay, so this comes from that. So it's really very simple to obtain one from the other. Just remove these fixed functions. And what's nice again is that these functions are supported only in small balls. Okay, so now we're going to prove a lemma, which is we're going to start kind of in reverse. Compute this integral over Rd, of the gradient of the potential, but not of the original potential, but this truncated potential. Because we knew that the one without the eta here is infinite. It's a divergent integral. But if we put back the eta, it's going to be convergent. It's going to have an interesting value. So it's going to be that 1 over, I think it's 2 CD. So CD is always this constant that's here. So I think it's 1/2 of sum of g of eta I converges as all the eta i's go to 0 to the energy that we define. Just checking I have the constants right, but I think yes. Okay. So in other words, you can write this thing as the limit of this guy, and that's the renormalization if you want. So this term is going to be finite now. But if you let eta go to 0, it goes back to tending to infinity. However, if you subtract off the correct very large quantity, the difference has a good behavior. Okay, so it's a sort of plus infinity minus infinity procedure, where you let the eta i's go to 0. So we're going to prove this. It's a simple computation with Green's formula. So let's start from this point. And let's integrate by parts. So there are some boundary terms at infinity, but my claim is that these terms at infinity are actually 0 because the system is neutral. You see the system being neutral when you look at the potential here that's generated by a neutral system. The function g, well, if s is positive, it decays at infinity, it tends to 0. And if this thing doesn't decay, when you integrate it against something that has integral 0, then it starts to decay because the behavior becomes the behavior of the derivative of g, and that also decays. So you can check that in all cases, h and eta tends to 0. So this guy tends to 0 at infinity, and also its gradients in sufficient ways. So you don't have to worry about having a term at infinity, and then you can replace this by h and eta, Laplacian h and eta, with a minus sign. And now we can replace by the formulas that we have. So let's think of what's the best way. So I'm going to write this as hn using this formula minus the sum of these things. And the Laplacian of h and eta, it's just this right-hand side. So it's going to be a CD. Yeah, so it's kind of the same computation I was doing earlier, except now it's correct. Okay, so maybe here we write it j, so we don't confuse with the i's that are here. And here eta I. Okay. Okay, so maybe let me start to explain while things dry. So the idea is that this term, when it hits delta xj eta j, there's two cases, right? Either I is different from j, so you have xi, xj, and you let the eta i's go to 0. So when the eta i's go to 0, you can eventually assume that the balls are disjoint, right? Ball radius eta I around xi, radius eta j around xj. Okay, so when they are small enough for each fixed configuration, so this is a limit for fixed configuration, you let the eta I go to 0, these balls are disjoint. Now this guy is supported only on that ball, and here you're integrating on this sphere, so you see nothing. This one is supported here, and you're integrating here. So there are no cross terms for these two. Now, if I equals j, then you're integrating, again, on the sphere, a function which f eta I was drawing it before. It actually vanishes on the boundary. So again, there is nothing. So this thing doesn't hit this term. And then you get these guys, which are okay. And now what we're going to do is to rewrite Hn in this form. Okay, so when things dry, I will do it. Should have these, German style raclette. I don't know how you say in English. I think for the windows, like that. Okay, so now I write that this is equal to CD. So Hn, I write it like that. The integral gx minus y, sum of delta xi minus mu of y. So that's to substitute for Hn. Gets integrated against that. And then this term, as I said, only gets integrated against this thing. So minus a sum from 1 to n of the integral of f eta I x minus xi d mu of x with an n. Okay. So by the way, this is because balls are disjoint when eta i's are small enough. And because the support of f eta is in B0 eta. Okay, so this allowed us to get there. And now we're getting close. So here, you see, again, you have to worry about I equals j. And then you have I different from j. So let's look at what happens for I equals j. So I have a sum over all i's. And here I get g of x minus xi. Yeah. Minus, yeah, so I forgot the minus here. Yeah. No. This is a plus, in fact. Okay. This is a plus because the minus Laplacian of Hn eta is equal to plus this. So this is a plus, and now it's a plus. Thank you. Okay, so I'm hating this one with I against this one with I. And then everything else, I have the sum for I different from j of double integral of g delta xi minus it's a sum and mu delta xj eta j minus n mu. Okay, and then the final term so what's going to happen to all these three terms? the first term, it's actually computable exactly, because this is something supported on the sphere of radius eta I around xi. So on that sphere, g is constant, and the value is g of eta I. Okay, so this thing, that thing is equal CD sum of g of eta I, because we've built things in such a way, right? On the sphere, you average on the sphere this is constant because of g of eta I. Second term, now the balls are disjoint because I have I different from j. I have a delta xi, I have a delta xj. I can just let eta j go to 0. And this thing just converges to the double integral with just the deltas. And of course the n mu also. So this is actually our term that defines f. So I can just basically take this out by taking the limit. And the last term, this is an integral that lives in a ball of radius eta. The function f eta I has the same singularity as g, so it's 1 over x to the power s, something like that. But mu is a uniform, mu is a uniformly bounded density. So I can just bound this thing. I can bound by the L infinity norm of mu times the sum, maybe a constant here, an n. And then I can just integrate g over a ball of radius eta I. This is not going to be that big. Okay, so because g is integrable, this thing goes to 0. I can even bound it for you because it's useful to bound it for later. Okay, so what is the size of this? You integrate 1 over x to the s. In a d-dimensional space, it's actually eta I to the d minus s. So I'm going to say this is less than c, and I have n squared because I have a sum. Or no, actually, I have n times the sum of eta I d minus s times the L infinity norm. If you want to keep the, that's if you want to keep the dependence on mu. You don't have to keep it. You can just put it in the constants. But okay, so I claim that when eta I goes to 0, this is fine because d is bigger than s. Okay, so if you put all that together, we started by computing this integral, and we found that it's some things that go to 0 plus a sum of 2 terms, the CD sum of g of eta I, and this term that's exactly fn up to dividing by CD. So we find exactly the lemma. Okay? Any questions on this? All right. So this gives us a way of giving a meaning in a renormalized sense. However, this is not quite the best we can do, and the reason is that this is not quantitative. Okay, it's a limit. But we can do something much better that is expressing really how close this quantity is from being equal to that. Okay, so the second idea that's going to come into play is a monotonicity idea. And it's related to what I was explaining this morning with Newton's theorem. So for now, we've discussed the case where you have smeared and the balls that correspond to the smearing are disjoint because eta i's are taken to be very small. So balls are disjoint. Now, if we sort of inflate the balls, right, make them grow, let them get bigger, we said that what can happen is at some point the balls can start to overlap. And by Newton's theorem, this is only going to decrease the energy. Okay, so now what we can do is we can let the eta i's be arbitrary, but we're going to have an inequality. If you increase the eta i's, the computed value decreases. Okay, so the way to do this, I'm not going to do the whole computation because it's kind of a bit similar to what we did here, but it's in the notes, is that if eta is bigger than alpha in the sense, for every eta, for every I, eta I is bigger than alpha I, you can compute grad h n eta squared minus grad h n alpha squared. And that is going to be, that's going to have a sign, essentially. So there's going to be some little differences due to these terms. So these terms are the ones that are kind of the errors here. Okay, so up to small terms. So it's this minus these terms, minus this, minus these terms, minus these actual terms. So, okay. So to prove that, what you do is, again, you integrate by parts. You apply the same type of Green's formula, and you check that at some point you get a term that has a sign, and this is nice. So the appropriate terms are the corresponding terms like that. So these are the renormalization terms, if you want. Okay, and when you let alpha and eta go to 0, okay, so when you let alpha go to 0, this one's going to converge to Fn, x and mu, because by the lemma. And this one is going to give you the result of the computation with some eta, which is not so small, some arbitrary eta. And the result of that is the following proposition. So again, for every xn, you can show that the sum over I of the sum over j different from I, g of xi minus xj minus g of eta I, the positive part of that, so I write underscore plus to denote the positive part of a number. This thing is less than Fn x and mu minus, so you put exactly what's in the left-hand side here. So grad h and eta squared minus 1/2 sum of g of eta I. And you have to add these correction terms here. Okay, I'm getting tight here. By the way, what are these correction terms? These correspond to the error that you make in the interaction with the background mu when you change the size of the balls. So when you change the size of the balls, the interaction with mu changes a little bit, and it's reflected here. These are the terms. So this is true for every eta. Now, it's no longer an asymptotic result. And it is telling you that the difference between that guy and its limit, f eta I, is actually always negative. Okay, so if you want, this one is always bigger than that one, because what's on the left-hand side is positive. So that's what I was saying earlier. If you inflate the balls, and if you decide that that's your computed energy, you're going to make a mistake. You're always going to be basically smaller in energy than the true energy. So this proposition, in addition, tells you something more, which is that how much smaller you are, you can in fact quantify, and you can sort of retrieve some bound on some energy, which is the energy of the interactions at very small scales. You see, this thing is only counting if xi minus xj is very small. So for the points, you have your xi, you have a ball, radius eta I. If this ball has seen other points here, then you start to count them. And then you can actually control the energy, the interactions of these very close points. Okay, so moreover, this inequality is an equality if the balls are disjoint. So if the balls remain disjoint when you grow them, let's say, then you make no error at all. This is all coming from this little idea with Newton's theorem, if you want. Okay, so. Okay, so I write this with equality if the balls bxi eta I are disjoint. Okay, so essentially if the balls are disjoint, you have nothing on the left-hand side. This would be essentially 0. And then you would have equality. Okay, so it means that this limit, it's not really a limit. It's if you add back this term in there, it's something that's like monotone and eventually just is equal to the limit for small enough eta i's. So that's going to be useful. So now we can make some interesting choices of eta i's. So notice here that, so this term you can consider as a sort of small error, because I've bounded it before in yellow here. So this term was n times the sum f eta I centered at xi d mu. So we bounded this by norm of mu in L infinity times n times the sum of eta I d minus s. So this term will be small as soon as the balls remain rather small. So you don't want to make these balls too big, otherwise you really start to mess up the interaction with the background. On the other hand, this term here, g of eta I, so it has a minus sign in front, it's going to become very, very negative if you if you make the radii very small. So there's a question of balance between these two. And you can see that the right scale at which to take your balls, your radii, is exactly the micro scale n to the minus 1 over d, which we discussed yesterday, right? It's the typical distance between points. So what happens when you make this choice? N to the minus 1 over d, well then g of eta I becomes just n times g n minus 1 over d. And what is g n minus 1 over d? Well, here we have to discuss whether we're in the logarithmic case or not. So the logarithmic case is always a little bit different because, you know, the log scales differently. So it's going to be equal to either n1 plus s over d if s is different from 0, because remember g is minus s power, so it's a constant times that, a constant times this. Or if s is 0, then this is the log, or minus log, and then this becomes 1 over d n log n, right, if s equals 0. So that's for this term. And what about the other term, the f theta, where we bounded it here? And now this becomes, so if I take for eta I n minus 1 over d, I find n to the minus 1 plus s over d for each of these terms. Right, so this is just substituting this guy. And I have to take the sum, and I multiply by n. So you get what? You get n to the 1 plus s over d. So in other words, when you make this choice, these terms and these terms become exactly of the same order. This n 1 plus s over d, except when s is 0, you have this extra log. So this is why it's also a natural length scale, and of course it's also a natural length scale because it's the interparticle distance. And so now I can write a corollary of this proposition. So because this is non-negative, and because this thing has a sign, I can write that Fn is bigger than these sums plus this sums. So for every xn, Fn xn mu is bigger than minus, so a negative constant times n to the 1 plus s over d. And if I'm in the log case, I have to add this 1 over 2d log n when s equals 0 and with a minus sign. And of course, this c here depends on the infinity norm of mu. So the way you should think of it is, really the natural quantity here is the sum of these two things. So when you're in the logarithmic case, this thing should always be added to Fn for reasons that are scaling reasons that will appear later. I think I will tell it to you later today. So this whole sum now is bounded below. And you remember I told you this morning that one of the problems with removing the diagonal is we lose the positivity of Fn. So we no longer know that Fn is positive. However, here we're proving that, okay, it can have a negative part, but this is not so negative. So it's almost bounded below. Because if you compare to the natural scale, which is n squared, this is much smaller than n squared. Okay, so Fn plus blah blah divided by n squared, which is the natural scale, is bigger than minus c. And now you can put n to the minus 1 plus s over d. And this thing is, this is little o of 1. And this is very small because s is always less than d. So it's a negative power of n. Okay, so for practical purposes, it's starting to look like Fn is almost bounded by a positive number, but in any case it's not, but it's bounded below uniformly. And what we're going to see is that this order n to the 1 plus s over d, it's actually the correct order. So typically, this is a bound from below, but you have a similar bound from above. For typical configurations, not for awful configurations. So if you give yourself configurations of points, you can always cook them up so that the Fn is infinite, or very, very large, because what you do, or you take your configuration, put 2 points very close to each other. 2 points very close to each other, they repel each other, you can make this as large as you want. Okay, so Fn is not going to be bounded above. It's bounded below, but it's not bounded above. However, for typical configurations sampled under the Gibbs measure, or for minimal energy configurations, it is bounded by the same order, but with a plus sign, of course. So that's what we're going to see soon. And this explains why I was saying earlier that this guy is actually a lower order correction to the leading order, which was n squared. Right? Because when you divide by n squared, you find something small. Okay, so good. So we have one first piece of information, and now we can get a second piece of information by making another well-chosen selection of the eta i's. So we're going to choose eta I to be equal to Ri, where Ri is defined as, basically, I want it to be the minimal distance to the nearest neighbor. So now it's really going to depend on the point. And it's going to be, so there's a 1/4 to make things really disjoint. And we're going to take the minimal distance to all other points in the configuration. And we're going to max it at n minus 1 over d, because that's the natural length scale, and we don't, you know, if one point happens to be very isolated, we don't want the ball to get too large. We want to stop when we reach n minus 1 over d. And so now the balls are disjoint. And of course, we keep the fact that Ri is less than n minus 1 over d. How do you do that? Okay. All right, so let's see what we get from there. This proposition that was just erased was saying that if the balls are disjoint, you have equality, and you have a bound from below by something. So I had a sum of g, xi minus xj, minus g of eta I, so it's going to be that is going to be less than Fn. Okay, I'm basically rewriting the proposition. So now I'm going to call it HNR when the choice of eta is R. Okay? So I'm going to look at a point xj that achieves the nearest neighbor distance to xi. So what I claim is that I can bound this below by g of, for each I, the sum over I, of g of 4Ri, let's say. Because, you know, if really this thing is achieved at the minimal distance, this thing is 4Ri. But maybe you are maxing at n minus 1 over d, and this is this. So there's maybe a g of n minus 1 over d positive part. So that I can say is less than Fn. What did I want to do? Yeah.
The disjoint force, did I need to know that that's an equality?
Yeah, that is an equality, yeah. I don't need to use it now. But yes, it's an equality. I'm just going to bound from above because I'm going to throw away this term. So I transform into an inequality. And now I have to add these terms. So it's going to be plus. And I have these other terms, which I said I can bound by C n 1 plus S over D, because the Ri's are smaller than eta i's, and those terms are of that order. Okay, so I've thrown away this term that has a sign. And then from there, I'm supposed to retrieve an information on sum of G of Ri's. And now suddenly I'm getting confused. So let me check my notes. Oh, I see. Okay. That's not what I want to do here. I want to do eta I. And this, and what I'm going to take is eta I equal again n minus 1 over d. So the Ri I get here from the nearest neighbor, and for eta I take that. And now I get this. And this whole thing is less than Cn 1 plus S over D. And this way you get a bound from above for the sum of G of Ri. Okay, so the eta i's that are used here are not the Ri's. They are the n minus 1 over d. So what you get is that all these things are bounded by Fn plus this thing. And then in the next step, we're going to apply it with the eta i's equals Ri's. Okay. So sum of G of 4 Ri minus G n minus 1 over D, positive part, that is less than Fn plus Cn 1 plus S over D. And so this is the size of both terms here that we discussed before. So here again you have to discuss whether it's the logarithmic case or not the logarithmic case. And what you're going to get in that in all cases of S, the sum of G of, so it's going to be sum of G of Ri is bounded by C Fn plus n1 plus S over D. That's for S different from 0. And G of Ri divided by n minus 1 over D is less than that if S equals 0. So remember, adding this term doesn't really perturb the order of Fn. Fn is at best of that order, so this is a good bound, and it controls the minimal distances between the points. See, so it shows you that Fn even though it has this neutralizing factor effect of the background, right? You have the positive charges, they repel each other, maybe the energy is going to decrease because you have this neutralizing background. Well, if 2 points get very close to each other, you're still going to pay a big price in Fn, because if Ri becomes 0 or close to 0, this becomes very large, and so Fn has to be very large. So Fn controls the small scale interactions, and you can have a few, pairs of particles that are very close to each other, but not too many, right? So if you start to have many of them, you're going to have a huge energy Fn. And now we're not done, because there's another step, which is now apply the proposition with eta equals R. So what do you get? Well, when eta equals R, the balls are disjoint. So yeah, so here I need to write an inequality, because now my balls are not disjoint. And now the balls are disjoint, so I have equality. But I'm not going to use it, in fact. I'm going to use that 0 is less than Fn minus 1 over 2 CD grad H n R squared plus 1 over 2 CD sum of G of Ri plus an order n 1 plus S over D, which is always there. And now what do I want to do? I want to take this term now to the left-hand side. I'm going to get a control of this term. That term is going to be bounded by the energy plus this. But now what do I say about this? Well, this thing, we just learned how to bound it. So from star, I'm going to be able to bound it again by Fn plus Cn 1 plus S over D, except maybe in the log case I have to take into account this extra term. And so the final inequality is going to be this. So we have a proposition so you see, when you write Fn, you write it as essentially the difference between two very large things, right? I told you this is like a plus infinity minus infinity. If you let the eta i's get very small, you don't control either of these terms. But if you choose eta I equals Ri, what this thing is telling you is that each of the term is actually controlled. They don't get very big. Neither of them can get very big. They are both of the same order as the energy, and that is going to be very useful. Okay, so the proposition is that you can control both. So you have this thing. So this is control number 1. So I'm just going to copy this, right? Or sum of G of Ri over n minus 1 over D is less than Cfn plus n 1 plus S over D. And this thing is less than C. And so here you have to put Fn plus, as I told you, you should always add this thing in the log case. Plus these errors. And this is true for all configurations again. as long as mu has a bounded density. Okay, so again, I'm repeating myself, but Fn can be understood as the difference between two terms, one term that could get very big and the renormalization term. But when you make this choice, Ri, the minimal distances, these two terms are actually each separately controlled by a constant times the energy. So where do I want to get with that? The point is, again, that Fn is a good metric. It really does control the difference between the empirical measure and mu. So Fn controls un hat minus mu. So how we're going to see that now? For instance, let's say I want to take a test function. And I want to integrate phi against the difference between the empirical measure and mu. Well, I'm allowed to rewrite this as, first of all, n 1 over n squared. 1 over n, integral of phi is equal to this, right? It's the same. Now this guy, my problem is I don't really control that. But I control it if I put back the truncations here, if I smear the charges. So I'm going to write this as 1 over n, integral of phi, the sum of the delta xi, and I'm going to use the truncation Ri minus n mu, plus the error that's made, which is integral of phi, sum of delta xi minus delta xi Ri. Okay? Now, the second one I claim is going to be small because the Ri's are small. If phi is smooth enough, this thing can be made small. And the other term is going to be small because we're going to use Fn. So let me show you. How can I re-express this thing? You see, this thing is just the Laplacian of the HNR up to constants. Right? This thing is exactly equal to that. Because the truncated field, its Laplacian is the one you obtain with the smeared Diracs. Okay, so this whole thing is equal to 1 over n integral of phi Laplacian HNR, okay, minus 1 over CD plus 1 over n times that. So how can I control these things? Well, here I want to integrate by parts. Again, use Green's theorem. So let's drop constants, you know, and this becomes this. By Green's theorem, I assume my function is compactly supported And this I can bound by, take your favorite norm of phi. So for instance, a Lipschitz norm. Right, so 1 over n phi Lipschitz and the sum of the RIs, because you take phi and you take the difference between the average of phi on a sphere and the value at the center. You can certainly bound it by that. You could even do better. But okay, and for this I'm going to use the fact that the RIs are not large, because I truncate them at n minus 1 over d. And for this one, I use Cauchy-Schwarz. Okay, so this is less than c over n. The L2 norm of grad phi, this guy, and now here we get, I don't know, the Lipschitz norm times n minus 1 over d. So you see this is small. And what about these guys? So here the L2 norm, and here this. Now this is the crucial term. This is the one. I told you, now we can control by the energy. So this is less than C grad phi in L2. And here I get Fn plus n over 2 d log n in the logarithmic case plus n1 plus s over d. And I can divide this by n squared and take the square root. Because you see here, I have to take the square root, and I have the 1 over n, so I take it inside the square root, divide by n squared. Okay, so now, if I control Fn, in particular if Fn is much less than n squared, then this term is small. And of course, this term is always small, and so this thing will be small. All right, so the idea is basically Fn does behave like the square of a norm, at least in some weak sense like this. Okay, so this is what we have shown. So what we've seen, we want to compare the empirical measure to mu. Basically, we control by some things that depend on phi times square root of Fn over n squared plus these little error terms. Right? So these are small terms, but even this term is much smaller. It's small when you divide by n squared. Okay, so Fn over n squared, the message is it does control a form of convergence of the empirical measure to mu. If you don't like this formulation with test functions, you can just try to evaluate this difference in some weak norms. And you can find that there exists some space of the form h to the minus sigma. So if you like Sobolev, negative Sobolev norms, if you don't, just keep that. But you can find a negative Sobolev norm, which is such that the dual of this norm embeds both into Lipschitz functions and into H1 functions. So you can control, in fact, a certain norm like that, such that mu n hat minus mu in H minus sigma is controlled by this. Right? And now this is quantitative. This is a quantitative form of convergence. Any questions on this? So this I have expressed for test functions. You can also do it for indicator function, so for test functions that are indicators. So there are results, they are in the notes, where you ask yourself, okay, given a ball, what is the difference between the number of points in the ball and the integral of mu? So it's the same really as integrating this. Right? This is called the discrepancy in the ball, as I mentioned the first day. This is the discrepancy of the R. Well, that also you can bound in terms of Fn. So, of course, there's going to be some Fn, it's going to be some square root, and some things like that. But so it's not only restricted to very smooth test functions. If you control Fn, you have some control on the discrepancy, which of course is going to be, it's only interesting if it gives you an answer that's much smaller than the volume of the ball times n. And it is much smaller typically. Okay, so it's not claiming to be sharp, but it's already telling you a form of concentration. Okay, the difference of number of points in the ball and essentially volume of the ball is much smaller than the volume of the ball. And same here. This is a small term as soon as Fn is not too large. So this is my sort of survey of chapter 4. Showing that basically Fn is an interesting energy which is coercive, which is almost positive, almost behaves like a norm. And we've seen that we've used this idea of truncation, monotonicity with respect to the size of the balls, and the idea of using radii that depend on the configuration. So the idea of using these RIs that depend on the configuration gives you this extra control that you would miss otherwise. Okay, so now I'm going to want to use these properties to deduce consequences at the level of the Gibbs measure or at the level of minimizers of the energy. So for minimizers of the energy, we already saw a lower bound for the energy. So now we have a bound from below on the minimal energy. And we're going to see soon that we have a corresponding bound from above. But now let's see what happens at the level of the Gibbs measure. So I remind you that this morning we split the Gibbs measure and we rewrote it as, maybe I should erase, are you starting to find the board too messy, or should I clean better? Clean here at least. So let me rewrite P and beta in the simplified, or if you want, reduced form that we saw this morning. So it's called K and beta of mu. So now what I'm going to study is things like that. 1 over K and beta of mu. And maybe this is not P and beta. This is, I think I call it in the notes Q of mu. Right? It's Gibbs measures of this form. after all, you can define that for any mu. And it happens that for our particular Gibbs measure that we started from, it's the same as that for the thermal equilibrium measure. Okay, so we saw that this morning, but after all, we can just study this more generally, given any reference measure mu. So this thing actually we sometimes call the modulated Gibbs measure. So it's modulated with respect to mu. Okay, and so what I'm going to try to do now is to give you bounds on the free energy. Bounds on log k and beta of mu. Okay, so first thing is we just learned a bound from below for Fn. So if we know a bound from below for Fn, it's going to give us a bound from above for log k, right? Because this is the log of the integral of e to the minus beta n minus s over d Fn. Right, so this is by definition this. So we immediately get a bound from above. So since Fn plus this is bounded below like that, we obtain, so I plug in this inequality into that. Plug in, take the log. The integral of mu is 1, so you just obtain this trivially. So there's going to be a beta n 1 plus s over d. Plus, so there's going to be a beta n over 2d log n in the logarithmic case plus c beta. And you see the n1 plus s over d nicely simplifies with this minus s over d, so there's just a beta n in general. Okay, so I think, let me just check I have my signs correct. Oh, so compared in the notes, I have a slightly finer version where I keep track of the L infinity norm of mu. Okay, but here I decided not to keep track of it, to just put it in the constants. Okay, so we have a bound from above. Not too hard now, because we've made this study of the energy. So can we complement it with a bound from below? So the bound from below is going to come from, the starting point is going to be to apply Jensen's inequality again, in a similar way to actually some stuff Jean-Christophe was describing, and also to what computations we did yesterday. Okay, so when things dry, I will show you. But the bottom line is we can obtain a very similar upper bound, almost of the same order. Of course, once you've obtained bounds on the log k, you can obtain bounds on the log z of the original Gibbs measure, because you remember there's a direct formula that expresses k in terms of z, or z in terms of k. So you can just plug that back in and be done. Okay, so this thing is, I erased too well. Okay, so conversely, Jensen. So starting point, we start from log. And now it's nice we have a probability here. So we don't have to worry to work with like the Lebesgue measure. We can really apply Jensen. And it's going to be bounded below by minus beta and minus S over D, integral of Fn and now this computation, that's very similar to the computation we did yesterday. So for that, we're going to have to spell out what Fn is. So what do we get? 1/2 the sum gxi minus xj. So I'm spelling out the Fn, g of x minus y, sum of delta xi, sum of delta xj, and I'm expanding everything. So you're going to get terms like that. Right? And then you're going to get twice the terms of the form integral of g x minus xi d mu of x, and there's a sum. Right? So that's the terms that have n d mu and then delta xi. And then the final terms is just like that. So this is a constant from the point of view of that. And all of that, you integrate d mu of x1, d mu of xn. Okay, so when you integrate against d mu, remember you're going to get terms of the form g of x1 minus x2, and you're going to have nn minus 1 of the same. So in fact, they're all the same terms, because here you get g of x minus xi d mu, and here you get the same. So all these terms are the same. It's just a question of counting how many there are. And so here you find minus beta. So I get this quantity. And I have here how many? So 1/2 n minus 1 for those. Here I have minus n squared because I have n and then I have n. And here I have plus n squared. And this one is over 2. Sorry. Plus n squared over 2. And so this is a very simple number. 1/2 n squared plus 1/2 n squared minus n squared. So the n squares disappear, and you only get a minus n over 2. So you get minus, so it's a plus, beta n 1 minus s over d over 2, double integral of g d mu d mu. Okay? And now there's two cases. So you see how it's kind of the same computation as yesterday. Two cases. Either g is such that integral of g d mu has a sign. It's positive, in which case this is positive, and we wanted a bound from below, and we're happy, actually. This is good for a bound from below. And that is the case if s is positive. So if s is positive, g is positive. And when you double integrate, it's positive. Unfortunately, when s is 0, this term doesn't have a sign. And this is going to give you an estimate. Okay, maybe this is negative constant. You get an estimate still. But this estimate is not sharp. We could do better. And to do better requires more work. So the work is done in the notes. But if you're in a negative S situation, what you have to do is you have to basically partition your domain into subsystems and use a sort of subadditivity property. And I'm not going to do it, but if S is negative, there is a better estimate to be found. And now I'm going to give you the conclusion with the better estimate, which is, so we have this bound from above and below. Now the conclusion is you can put an absolute value here. Now it's going to be a bound from above and below. And here, instead of beta n, which was good, you get a slight deterioration in terms of beta. So it's a deterioration that happens only when beta is small. Okay, so this is the estimate. So I have to define this chi of beta. So here I write better estimate exists by subadditivity. Already, if S is positive, this is sharp. Okay, so the final estimate and what is chi of beta? So it's just 1, so it means it changes nothing if beta is bigger than 1 or S positive. So that's what I told you. If S is positive, the estimate is as good as this. If beta is bigger than 1, it's also as good as this. And if beta is less than 1 and S negative, there's a formula for chi of beta, which in the logarithmic case, it adds a logarithmic correction. And in the lower values, it's beta to the S over D minus S. Okay, plus 1, log beta plus 1. Okay, so if you're in the case S equals 0, then this is just 1. So it's a log beta correction, which only hits when beta is small. And if S is really negative, then you have an extra negative power of beta. So the reason why I have all these details is because I worked hard at getting estimates that are explicit in beta. So that if you want, you can play with letting beta depend on n. Because the C here is independent of beta. It depends only on mu. So this is valid for all beta, possibly beta depending on n. Okay, and so this is why you have to pay attention to this degeneration of the estimate when beta gets very small. And actually, I believe that this thing is really there. It's not just a sort of artifact of the proof. Okay. So now I'm going to try to tell you in 1 minute how this thing gives you concentration. So first of all, it gives you it's an interesting estimate per se, right? To know what the free energy is. We saw that log Z, the leading order was n theta. And this is a sort of next order term, which is much smaller. Because this is of order n beta, and n beta is much smaller than n theta if you pay attention to what it is. And the second thing that you can get from it, maybe I'll do it here, is that when you control the free energy, it gives you an easy way to control the exponential moments of the energy. So control exponential moments of Fn. Maybe I do it here. Okay, so let's say you want to control the expectation under this law Qn beta of mu of e to the beta over 2 Fn. So by definition, what is that? So this 1 over k, so the partition function, the integral of e beta over 2 Fn, e to the minus beta Fn, d mu tensor n times, right? This is the expectation of this under, that's the form of the Gibbs measure. And of course, this beta over 2 was not chosen accidentally. It's chosen so that, well, it's strictly smaller than beta. So in particular, here you get beta over 2 minus beta. So this is equal to 1 over kn beta integral of e to the minus beta over 2. I forgot my n to the minus s over d. To put it everywhere. And what is that? Well, you recognize this form as being the partition function, but for beta over 2 instead of beta. Okay, so this is in fact kn beta over 2 divided by kn beta. But this is a general fact, by the way. This is valid for any energy. You can put any form for Fn, and this is always true. So if you want to control the exponential moments of your energy for not too high powers here, you can always do it by controlling the ratio of partition functions at 2 different values of beta. And so now, can we control the log of that? Well, we have upper and lower bounds on the log of k. So we can certainly control the log. So hence, the log of these things. So plus beta over 2. So here there's a plus, that's what's important. Now this thing we control by log kn beta over 2 plus log kn beta. And for both of these things, we can apply the estimate here. Okay, so I'm going to say it's less than c beta chi of beta. And neglecting the s equals 0 case for now, you could just put back the n log n in addition to this one. Okay? So what this is telling you is it's telling you what I was trying to say earlier, that for typical configurations, Fn cannot be too large. Because basically, Fn gets bounded by n 1 plus s over d by this estimate. Because if it's not 1 plus s over d, then this thing is going to be bigger than n. And you're going to get a contradiction with that. So up to the chi of beta. Okay, so with Markov's inequality, you're going to get that this is true, except with small probability. And so this is what I was saying, that the order n 1 plus s over d is actually correct from below and from above as a correct bound for typical configurations under the Gibbs measure. And you remember, if you control Fn by that, then you have concentration. Because mu n minus mu, the empirical measure minus mu, is bounded by some constants that are essentially like that. And so this is going to be less than n minus 1 plus s over d square root. Right, so you're going to get small quantitative control on the difference. And so this, I claim, is a concentration estimate near mu. And from this estimate, you can also obtain that there exists at least one configuration for which Fn is less than that. It's kind of obvious that there exists at least one. And so the minimum value is certainly less than that. Okay, so now if you want other bounds, so this whatever norm that is not very precise, but you can make it precise. You can control concentrations and also discrepancies in balls thanks to these estimates. So you see, it wasn't the ingredients that came into this were this electric rewriting of the energy, this definition with truncations, this renormalization by truncation that gives you a bound from below, and then plugging that into the Gibbs measure after splitting, and just using these little Jensen's inequality arguments. Okay, so relatively quickly you can get to these estimates. That this is really the next order part of the energy, and it's of smaller order than the leading order. Okay, that's all for today.